Welcome back. Hopefully you had a good weekend. We're starting into section 10.3 tonight. Just to give you a little clue about the schedule for this week. Tonight we'll do a very brief introduction to section 10.3. It's actually a fairly short section. Tomorrow I'll be posting a video with some additional examples. So in this section you'll have both a written set of examples which are currently posted, but I thought it'd be helpful to go over a few more in more of a video format for this. Wednesday, you'll see section 10.4 presented, and Thursday, you'll see examples from 10.4 again. We'll split it up, have some examples in print and some in a video presentation. So let's get started here. First of all, we want to remind ourselves something about sequences. Remember, a sequence is just a list of numbers. A series is the sum of the sequence. So suppose we have a sequence where all the terms are positive. And then we want to look at the series associated with it. So we want to look at the partial sums. And since all the terms are positive, every time you add a new one in, it makes the partial sum bigger. And so S1 is less than or equal to S2 is less than or equal to S3 and so on. So the partial sums form a monotone sequence. That means each term just simply is at least as large as the previous one. Now, a fact that we barely covered in 10.1, but which is important here, is if you have a monotone increasing sequence and you have it bounded above, then it has to converge. So if you're always moving up and there's a ceiling above you, eventually you're gonna have to stop going up. That's basically what this one says. It's important to note that when we're talking about the series converging, we're talking about the partial sums. Those will always be getting bigger. However, the sequence, the a sub n's, is likely getting smaller because obviously if it doesn't go to 0, we know the series can't converge. Okay, now we come to the main topic for this section. It's the integral test. You won't use this directly all that often, although occasionally it comes in handy. However, it is going to allow us to get one important result that we'll use in the next sections. Right now, all we have for convergence of series is we know that the terms have to go to 0 if it's going to converge. However, that doesn't prove that it converges. It just says it might converge. We also have our formula for the sum of a geometric series. But right now, that's about all we have. So this gives us our first real test for convergence. This applies, first of all, we have to have a function that's always positive and that is decreasing. And our sequence is defined by this function evaluated at the various whole numbers. So that's a pretty restrictive set of conditions here, but it does handle some really nice situations for us, as we'll see. So in this case, where you have a sub n being some function of n, where f of x is always positive but decreasing, the series converges if and only if the integral from 1 to infinity of f of x dx converges. So we create an equivalence between a series converging and an integral converging. And back in section 8.8, we worked with that integral. Now, it seems like a long time ago because that was back, before we had to adjourn and move off campus. So you might want to go back and brush it up. Also, if you still have your 8.8 homework, I did create a drop place for it so that we can get that collected and in. Now, while this is a helpful theorem, it might require you to be able to evaluate some integrals, and those could be tricky integrals, as we've all seen in the past. So let's go to the main place where this is used. This is what's called a p-series. Okay, a p-series is a very special kind of series. So the p-series is when you have a sum of 1 over n to some power. So 1 over n squared, 1 over n cubed, and so on. And a p-series is going to converge if and only if the integral from 1 to infinity of 1 over x to the p dx converges. That's using the integral test because 1 over x to the p satisfies the conditions. It's always positive and it is decreasing. Well, we can carry out that integration fairly easily. So the integral from 1 to infinity of 1 over x to the p, remember that's just x to the minus p. We have to interpret that as the limit as b approaches infinity of the integral from 1 to b. And that's just a power rule. So we get b to the minus p plus 1 over minus p plus 1, and then evaluate it at 1, you get 1 over minus p plus 1. And we want to see, well, when does this converge? Well, it's going to converge if this b term goes to 0, which is going to happen when its exponent is a negative exponent. Okay, so that limit's only going to be finite when minus p plus 1 is negative, or another way of saying that is p has to be greater than 1. So a p-series converges if and only if the p is greater than 1. Now notice this does give us some examples of cases where terms can go to 0, but the series diverges. So if p was 1/2, we would know that the p-series diverges, and yet 1 over n to the p would be 1 over square root of n would be going to 0. So the terms would be going to 0, but the series would diverge. So again, the nth term test only works to show divergence. It can never show convergence. One thing I did want to point out here is we're going to chop a little bit off this section. It's not a terribly useful little fact at the end of the section. So that error estimation material on page 585, you can ignore that. It really doesn't help us a whole lot. So that's all we'll have for the integral test. And of course, you want to read through the examples that are out there right now. And I will post a video with some more examples tomorrow. The homework for this is set to be due next Monday, so there should be plenty of time for asking questions and so on. So take care.